matches, and in this case, let's say these two, right? And then you look at which products or services this person has not consumed yet, right? And so these are these two people's recommendations. And from that, you extract the things that this person hasn't. Okay, what this is showing is that out of these two, this one matched a little better. And so you get the recommendation from that. Well, no, sorry. So, actually, it can mean either that or that it's an average of these two. Actually, we normally create a subset like this from which we extract recommendations. We will see that in the next few slides. Right, so fundamentally we weight all users with respect to similarity with the active user, and then we select a subset. How do we select that? We will talk about that a bit. So, and these are often called neighbors. And this will ring a bell because we also talk about K nearest neighbors. Now, whether it's K or some other method, we will see what we do. So we normalize the ratings and compute a prediction from these weighted combinations of selected neighbors' ratings. And we present the items with the highest sum number, highest n predicted recommendations. So the common way to figure out correlation is, of course, Pearson correlation, right? For ranking, we have a thing called Spearman correlation, but since this is rating based, it's Pearson correlation, which is the covariance divided by standard deviation, product of the standard deviation. The covariance formula and the standard deviation you should be familiar with. Right? We may then want to weight, right, the more important recommendation. So, for instance, we may want to have a weight here shown as S. Actually, the complete weight is shown as W, but it contains this thing S, which says that if you have, so it's like a threshold. If you have at least, say, 50 in this matching region, then you give a full weight. Otherwise, you give a partial weight. Right? So if only 25 are in this correlation set, then this becomes half. Right? So the weight is half of whatever the correlation you have computed. And how do you do this? Of course, is in this case, is just an example. This will depend on the amount of data you have. Right? So obviously, for Amazon, they can do something much greater than this number. But for some others, we may have to reduce this number. So here's how you select that subset, neighbor selection. For a given user, select correlated users as their subset for predictions. And these are two common ways to do that. The first is probably the more common. So you use the most similar end users, where the weighted correlation is closest. The weighted correlation is highest, the highest n with weighted correlation with the current user. Another way is, of course, rather than having a maximum number of users for the set, you can have some kind of threshold all those who are have a greater than this amount weighted threshold. So sometimes it may be 100, sometimes it may be 10, and so on. Right? So that's why this other method is more commonly used, because you will always have a similar number, and so you can compare easily. And then, of course, based on that, right, you still have, so based on that, now you have some neighbors, right, the neighborhood, but each of those will have, each of them will have different ratings. So you need to see from that subset how to match in some way the user's average rating. Right? Now, these are all close to your this particular user's profile. They are close to him or her, but you want within that to be able to still rank, right? Or rate. So we can use weight the users' ratings, the other users, the neighborhood users, by how similar they are to the active user. And by active user, I'm meaning any returning user to the site. Right. Now, of course, you may have realized there are some problems. The first problem is the most obvious, right? And it's called the cold start problem. So what happens if a new user joins, right? A new user joins, so it's there's no, sorry. So the first thing is there has to be some kind of critical mass in your system, right? If there are not enough other users already in the system, then it's going to be hard to find a match. Then the sparsity is about the number of items and the number of users. So the cold start is mainly about the number of users, but sparsity is, so even if you have a lot of users, there could be some products or services where there is no feedback, no ratings. So our data matrix becomes sparse. So here you have user 1, user 2, and so on. And then on the other, in the columns, item 1, item 2, item 3, like this. So if this matrix has a lot of zeros or blanks, then you can imagine that you're going to have a problem. So first rate problem is that you cannot recommend an item that has not been rated by anyone. So for instance, new items or kind of esoteric or rare items, right? So there may be people, right, who I don't know, like this particular antique something, right? But there are not enough such users. All the people are coming for modern things, and so there's no one to rate that. And first rate is also related to new user, right? A new user who has no profile, right? And that's why usually these systems would ask a new user to give their preferences, right? At least in a very broad way. These are the areas I'm interested in. If it's books, right, I'm interested in, I don't know, adventure or science fiction or romance or I don't know, whatever, technology and things like that. Now, most of these are technical problems, right? This it is partly technical, but also has a ethical, philosophical kind of implication, and that is about popularity bias. We cannot recommend items to someone with unique tastes, right? Because trends only recommend popular items. Now you may think that this is not a big deal, but ethically and philosophically, there is a big implication of this, right? And of course, this affects not just recommendation systems. If you think about Google search, right? It's the popular. So you, let's say you search for, I don't know, Omicron, right? COVID, Omicron. So the top sites are the ones that are popular, right? That means ones that most people are pointing to. And generally, because of the so-called wisdom of the masses, this is okay. But there may be, say, if a non-mainstream idea about Omicron is important, right? It won't show up. Right? So one of the common thing about Omicron that is like has got a lot of hits is that it spreads 2 to 4 times faster than the Delta variant and so on, right? And so it has a R naught of 3 as opposed to 1.2 or 1.5 or something. So lots of articles about that, right? But there are a few articles that say, well, actually, we still don't have enough information about the severity of the disease caused by Omicron, right? But there are people who have looked at past pandemics like the Spanish flu and wondered, okay, how come Spanish flu killed 50 million? Okay, this is now, like less than 1/10 of that, right? What happened to the Spanish flu? So they've looked at that and they said, well, that's currently what we call the flu or influenza is that, right? So how come we are not dying from it, right? Nor do we get vaccinated. Well, in some countries they do give a vaccination, but we don't, right? So they have figured out, right? Okay, maybe the way pandemics end is kind of nature's own way or God's own way or whatever it is, that the more virulent, the more fast-spreading variants become less harmful, right? And so the more widespread. So now in some countries, Delta is only about 10% of the cases or something. 90% are Omicron. Right? And so we still don't know, we still don't have the data. But if that is so, then this is actually good news, right? Omicron is like good news. It's come to save the world, right? It's come to save the world, something we couldn't do ourselves by vaccination. Right? Now that kind of idea will never show up in a Google search, right? Because it's not mainstream, it's not the popular story. Right? Now, of course, you may say, right, there are so many people saying, that this vaccine has, I don't know, chip in it and all that. And so those are also alternate views and they are not coming on top. Right? So that's where it becomes really hard to distinguish good non-popular items from so-called conspiracy theories or fake news, right? That's a hard thing. And hopefully in the future we will have technologies to deal with these. Right. The second aspect, so the first aspect is using other users, right? Wisdom of the masses. The second aspect is content based, right? Uh, and so these are recommendations based on information on the content of items. So if it's a book, things like, the author name and the title and the keywords and even maybe the preface or reviews, things like that. And so here we don't look at what other users say. Well, we may look at what other users say in textual form, but we don't look at their ratings and things. We use machine learning algorithms to induce a profile of user preferences based on textual features. Right? And so this is related to text analytics. Can I see a show of hands of any of you who are doing the natural language processing course? Or is that not offered to the IS people? Okay, one person has. Did we finish it, or I have forgotten now? Was it last year or last semester?
Last semester, sir.
Last semester, okay. Right, so only one person. So there we discussed this whole thing of how to get textual content and so convert to features. I will also put in a task, but I will probably not. All these tasks will not, I won't ask you to kind of submit, right? But you can do them, right? So, So some advantages because we are using feature descriptions instead of other users' data. There's no cold start or sparsity problem. Right? No need of data from other users. Right? It also can make recommendations to users with unique tastes. Right? So there's a person who likes a book that not many people like, but the content of the preface and the title and keywords and all don't change, right, based on the user. And so you can still recommend based on their interests. So it's related to that, able to recommend even unpopular items because we don't have this first rater problem. And in addition, there is a kind of some explainable AI-ness to this, right? Explainable AI-ness means you can provide, if somebody asks, why are you recommending me this? Right? You can say, because of these features, which kind of are learned by the algorithm. And so those who did the NLP course will probably those who did the NLP will know that. So we did a small task how to predict the gender of Sri Lankan names. Right? You give a name and you try to predict the gender. And it's not clear how we do it, right? and sometimes we also get it wrong, but we can train a machine learning model and then ask it what are the important features that the model uses to distinguish. And you can see, okay, this, so you can make sense. Okay. So for singular names, for instance, there is a E kind of sound at the end in many female names, right? Things like that. Okay. So the main, well, this won't be a disadvantage, but it used to be a disadvantage, but now there are some standard techniques to encode meaningful features from text. And user space must be, so this is a little trickier. User space must be represented in a function, as a function of these content features, right? So user tastes have to be mapped to these content features. And of course, what collaborative filtering, the strong point of collaborative filtering is not exploited in this, which is the ratings of other users. They can, of course, you can try to incorporate them into the content features. Right? And in fact, that's what many systems do. So what are the content? Well, the content will depend on the domain. So for books, for instance, you have author, title, editorial reviews, customer comments, textual comments, like subject terms or keywords, other authors, the co-authors, for instance, and titles that this author has also written, and so on. There are interesting applications of this, right? For instance, which you may have also seen. I don't know if you use a site like Amazon to search for books, right? So you have this rate bias, right? So you see this book on, I don't know, let's say recommendation systems, right? And then there's a reviewer who has absolutely trashed it. Right? Said, you know, this book is not very useful and this and that. Right? Now, there's another book, recommendation system, and there's a fairly good review, right? But not by that other reviewer who trashed the other thing, by some other reviewer. Right? So now you have an interesting problem. Okay, there's book A has been trashed by some author X. Book B has been praised by author Y. By critic reviewer Y. It's impossible to figure out now. The only way to do it is go to reviewer X and make a profile of him. You know, what kind of person is he, right? So maybe he's very strong book critic, and so his critique of book A was actually very mild compared to his normal critiques, which means it's a good book. Right? On the other hand, book B, the author Y has given a positive thing, but you go look at author Y's profile and he has given every book very positive. So that the book B positive thing is not so positive, right? So, and if you think about it, last year one of your seniors did a project on this. This is quite similar to what happens, let's say, in your final year project grading, right? Because we have multiple graders, and so someone's slightly negative mark compared to their other marks may be actually not negative, right? Whereas someone else is giving a high mark compared to the other projects may not be very high. Right? So interesting applications like that there are also. But here we are not looking at that. We are it's a simpler idea. We take all this and we need to figure out how to extract features, but before extracting features, we have to extract the information. So author, title, those things, right? So if you are going from using a web page, either using an API or using web scraping, we have to do this first task, right? That's not really related to recommendation systems. But using that database, right? So this process requires this is information extraction. This process requires feature extraction, right? Or feature representation. So we need to represent these features from this extracted information and train a model. And we have to, of course, build a user profile, right, based on their likes and dislikes. So this is where, this is the weak part in content-based system. So we may plug in some collaborative filtering here. We will see how we typically do. Right? So then, in this example, maybe you ask the user to say what genres they are interested in. Whether they're interested in science fiction or technology, or and maybe sections under technology and so on. Right. So here, this is basically showing the extraction, feature extraction part. From this book, we want the title, we want the author, we want some description like this, and below this there will be some reviews, editorial reviews and things like that. So you extract the information like this: publication date, reviews, comments, and so on. And then from this content, we can create what is called a bag of words, vector representation, right? And now these are a bit more sophisticated, so you can build things like word embeddings, right? So whatever feature extraction method you use, after that we use one way is to use a binary classification. So anything that has a rating of more than 6 as positive, and less than 5 or less negative. So you have already seen how you can train a naive Bayes. We use naive Bayes for numeric data, I think. But since we have now converted our text data into numeric vectors, then you can train a model, right? So if you think about it, what we normally do for data mining, data analytics, and so on, are now referred to as tabular data. Right? Tabular means in tables, you have different columns with different data types, right? So one column may be height or weight or BMI or something. Another one may be the gender, right? Another one may be an ordinal variable like income level, low, medium, high, and so on. So they're kind of heterogeneous data. Whereas if you're doing problems like for text or even image, right? For text, good ways of vectorizing text are fairly new compared to images automatically are numeric vectors, right? Because you have positions and intensities and colors and so on. So if you think about these kind of data, they are in a way homogeneous, right? So they are numeric vectors, and so tabular data has different columns having different data types, right? Including Boolean and numeric and categorical and so on. But in a text or image data set, these vectors will all be numeric. Okay. And of course, the kind of algorithms that work better for text are a little different to those that work better for images. So after you do this and train naive Bayes, or you have a whole battery of algorithms now available in any tool that you use, whether you use RapidMiner or a library like scikit-learn. And this learn profile is then used to rank all other books as recommendations. In naive Bayes, we have this idea of priors and posteriors, which kind of works nicely in this case. So you can work out a prior probability, right? That's common for all, right? All the users. And then we saw that naive Bayes is based on a conditional probability, right? So the posterior is given this user. Right? So in general, we have a general idea that these are the most popular books, right? And these are the next popular, and so on. But given this particular user, maybe this one becomes more highly recommended. Yeah, so this is basically explaining the same thing. Bag of words vectors. I will set a small task on text classification, which will hopefully give you an idea of what we do with this. We remove things like stop words, which are like, these are function words that are that add noise, right? And the to and so on are all just in every document will have those. So we need to have some way of removing those. And we also saw Laplace's smoothing, right? Because to avoid those zero probabilities. If you came for last week's, sorry, not last week, week before last. I hope nobody came last week for the lecture, because it was supposed to be an educational experience at the ICTA conference. Can I see a show of hands of how many of you attended the conference? Were you not sent the links, the Zoom links? Can someone unmute and say whether you were sent the Zoom link for the conference? Prashant, were you sent the links? Yasas, So you send the links for the ICTA conference.
We got the links, sir.
Okay, so you were given, but you haven't attended, right? I know some of you are busy with your projects, but actually, those are the kinds of experiences that expand your kind of experience. And because it happens every year now, people have kind of taken it for granted. But since you're involved in a research project, all the more reason you should have. I mean, there are lots of ideas that you can get, right? Even for your project, you could have got some ideas, right? Okay, because somebody else has done a project, not even your project, right? But the technique he used give you an idea you can try with your project. Okay, so I mean, beyond that, the details I will are in the tutorial-like thing that you will do. Probably one of the most important things is that these two techniques have orthogonal benefits and disadvantages, right? So, or complementary, right? So, the ones that content-based filtering is weak at, collaborative filtering is better at. Those areas where content-based is strong, collaborative methods may be worse. So obviously, this is the idea for having a hybrid approach. And today, I don't think there's anything that tries to use only one of these, right? So the way you combine can be different, right? So apply both methods and then combine recommendations at the end, right? So you will have to have some kind of weighting system. Using the collaborative filtering with data that is content-based. And the opposite of this, use content-based predictor as another collaborator. So collaborators are all the other users and content. So again, there has to be some weighting of because content-based should not be just yet another one collaborator. And this is probably the most common. Use content-based predictor to complete the collaborative data that you have. Okay, so this is trying to show one of those, right? So you have movies, and from IMDb, you do a web crawl and create this database information extraction part. Also, each movie has a user rating. Based on the movie content, like the synopsis and various things, you build whatever the predictive model using the user ratings. So this has a full user rating matrix now, and then we use collaborative filtering to match some user who logs in with this data, right? So, so even if it's a new user now, there will be some default priors, right? No posteriors, but the priors. And as the user interacts with the system, you will start building a profile, and then you can use the collaborative filtering to give recommendations. So this avoids the cold start problem, because you already have this for any new user. So there won't be any collaborative filtering. You just take from this user matrix and recommend. But as this person then starts, buying books or watching movies or whatever, their profile can be correlated with those in the system, and then more accurate recommendations made. The metrics, yeah. So if you have numerical predictions, right, where you're actually saying this is likely to be, I don't know, but based on the probabilities, you're saying this is like 0.78 or something. So then you need to have numeric metrics like mean absolute error. Otherwise, if you're just saying, ratings like 0 in a Likert scale 0, 1, 2, 3, 4, then you can do obviously F1 measure or area under the curve and things like that. Some people also do things like paired t-tests for statistical significance, whether to add something or not. In very large systems like Amazon or Netflix or IMDb, you may have to do sample selection. That means you don't want to basically active learning is an idea that you sample. So I don't know whether we have talked about, maybe not in your class, right? So if this is the entire sample space, if you kind of obviously, if you can't afford, right, design millions, you can't afford to do that, right? You want to have some way of making sure that your sample is representative. So your sample is not like all data points in this corner of the space, right? So there are techniques to make sure that is more representative. Things like uncertainty sampling, committee-based sampling. Active learning is about using some information to make sure that the samples are as far apart as possible. Right. So basically, if you think about it, recommendation system is another way to combat information overload. This is the problem. Otherwise, if we could, of course, read all the reviews and make an informed decision, that would be the best. But that's just physically not possible. So we use machine learning to help us. And once the recommendations come, then, of course, we can go and read the detailed reviews of those recommendations. And that's what we tend to do anyway. Right? Collaborative filtering is powerful, but has some limitations. And many of them are addressed in content-based filtering, and therefore they complement one another. Right. So you will, in the hands-on, you will try a very simple collaborative model, and then try to improve it until you get a fairly decent model. Right now, so let's see how are we for time. Right, I have said I will use only 90 minutes. Let me see if I can keep to that. So the second kind of area, because if you remember, I said we will use 3 of these sessions, the first 3 sessions. That means week before last, today, and the next one, to look at this kind of graphical tool, and which helps us to increase productivity, right? Because you can very quickly put together a workflow and then run it multiple times. And the next 3, which is in January, right? I think you have a 10-day break or something like that, or 2-week break, and then in January we have 3 sessions. We're going to look at what happens when in all these things we are talking about now, the application and the data has to fit into your computer memory, right? So in the 3 sessions we'll have in January, we are going to look at what happens when that assumption is violated. And of course, very often it's unlikely that you're going to quit all your other running applications and only do this, right? So it's even less than that. The amount of data you can handle is even less than that, right? But when we look at situations where the data is cannot be kept in one machine, we have to think about cloud computing. So the next 3 sessions in January will be on that. Right. So let me. These are slides adapted from a different graphical user system called Orange. And if you want, you can obviously use that, right? Orange can be very easily downloaded and used. Or you can continue with RapidMiner. We're going to look at 2 main algorithms, but I'm introducing them slightly differently. The first as exploring the data, and the second is production level clustering. So first, data exploring, right? If you think about it in general, if you're given like a bunch of numbers, you want to have an idea of the data, right? We do things like range, mean, variance, distribution. Those are the kind of things we want to know to summarize the aggregate behavior of. Right? So if I have 100 numbers, it doesn't make sense to my brain. But if I know, well, the average of those numbers is 62. Right. So then I know, okay, right. So all the numbers are going to be spread around this, but how far are they spread? So I need to know. Range. The range basically says, okay, so all of these numbers are between 17 and let's say 91 or something. Right. So range, and the mean is here, average, and then I want to know how these are distributed. We normally kind of think, right, so this should be like this, right? Very few 17s, very few numbers less than, let's say, 25, and very few greater than 80 or something. But this is not the only possibility, right? So other people will say, yeah, the other possibility is like this. Yes, we are still within a certain box, but this means, of course, the spread is less, right? The variance is less, the standard deviation is less. But of course, that's not the only way it can differ, right? It can, for instance, be multimodal, two modes, right? Things like that. So we want to know what the distribution is. But all these only account for what is called aggregate behavior of the data, general behavior of the data. And that's why when we want to find out more, we have to do things like clustering. So clustering can be used as a way of exploring data. Because we want to also know about individual data points and their relation to other points. Right? Finding similar data points. And this similarness requires some definition of distance. Right? And so you can imagine that if these are in this one, which is the integer number or real number domain, right? If that is the data, then we can easily measure distance, which is just the difference between numbers, right? But in general, we will have more than one attribute, right? So even if you have two attributes, right, then you start requiring distance measures and distance measures like Euclidean. So if you have two features, right, f1 and f2 or x1 and x2, then you may need to define the distance between 2 points in this feature space. And what we normally do is we want to define this distance, right? This as distance, and that's referred to as the Euclidean distance. Right? And we know that it's using the Pythagoras theorem. It's the square root of that plus this square plus this square, right? And we can, of course, fairly easily extend it if we have three variables, right? To say it's the square root of this squared plus this squared plus whatever the distance in this other direction, right? So in general, and if you have like many, right, we can say the distance is the square root of all those squared terms. Right? We can't draw them, but we can compute the distance. Right? So x1 squared plus all these things, all the terms until xn squared. So we know how to compute the distance, Euclidean distance for any number of features. But there are other ways. For instance, you can say the distance is actually not this dotted line, it's actually this line, right? Or this line, Manhattan distance, so-called Manhattan distance, and so on, right? But let's, for the moment, just think about Euclidean distance, which is the most common for numeric data. And you can do it for, I don't know, 1,000 variables, it doesn't matter. but actually we want to know, what we really want to know is not the distance. We need the distance metric, but let's say after that, in clustering, what we want to know is whether there are like groups like this, right? That means clearly identifiable clusters. We want to know that. Right? So how do you do that? Right? So we want to know how far this cluster is from this cluster, right? Because we may not have nicely separated data like that. We may have also points in between. So I want to know which clustering will make sense. Right? So for instance, this point, should it belong to this cluster or this cluster, which will be better? Right? So for that, we have ways to kind of measure the distances. This is a single link method. You basically find out the two closest points and find the distance between them. Complete link, you find the two furthest points and find the link distance between them. Average link is where you find the average distance between members of this cluster and the other cluster. And it turns out that these things give slightly different results. Okay, I have put orange here, but the same thing should be there in bit minor. Right? Should be able to say as a parameter, single link, complete link, average link. Right, so once we have the notion of distance, it's easy to conceptualize hierarchical clustering. So I'm assuming we have, these are the data points, right? Each of these data points can have any number of features, right? So let's say we have, I don't know, 17 features in each. But now we know how to compute the distance, because the distance is simply square root, so the square root of x1 squared up to x17 squared for each of these points. And let's say we find that B and C are the closest. So we put them in one cluster. So you can imagine, initially they are all in their own, within quotes, clusters. But we say B and C are close together, so we put them in one cluster. The next closest is D and E, so we put them in one cluster. The next closest is F with D and E. Right? Once you put them in a cluster, they are not available separately. Right? So at this point, you have A, B, C, D, E, and F. And out of those four, the closest is F with D, E. So you have D, E, F. So that's one cluster now. B, C is one, and A is another. Out of those three, the closest is this D, E, F, and B, C. So you have a cluster here now, and finally you have A. So this is where we start with points belonging to the own cluster, and then we merge two clusters that are closest to each other, and you repeat this process until you end up with one big cluster. And this is why it's called a hierarchical cluster. Right? We can actually do the same thing the other way. We consider everything as belonging to one cluster, and then try to find one that is most dissimilar to the others, and it will be A. So we separate A and the rest. Then you find from the rest what is the most dissimilar, and you find that BC is dissimilar to this, so you separate them. Right? So this is called divisive hierarchical clustering. What is explained here is called agglomerative hierarchical clustering. Okay, yes, so there's agglomerative is bottom up, divisive is top down. Sorry, so there's an example here, right? This is an example, I think, from this. No, it's not from this, it's from somewhere else. So it doesn't matter the example. So in this example, for instance, now we have hierarchical clustering. And of course, we set out to find out, which groups of points go together. So we have multiple answers here. If we cut off at this threshold, then we have 3 clusters, right? We have this green, this blue cluster, this other blue cluster, and this red cluster, 3 clusters. If we go further down, we have 4 clusters, these 2 clusters and these 2 separate clusters. If you go even further down, we have 5 clusters. There's 1 cluster here, 1 here, 1 here. Then this is 1 cluster, this is another cluster. And if you go further down, you will have more and more clusters. Right, so I put a link here for a sample data sets. This is, of course, a very, very simple, naive data set of students and their marks. Just to do a hierarchical cluster and see how they can be clustered. Right, so the fundamental thing is what clustering is not. Clustering is not classification, and by that, what I mean is, in classification, we know, or we assume, right, the number of classes. Right? So if you think about it, let's say you have a nice data set, with a label data set with 7 classes. Now we don't know whether in that domain there is an 8th class. We don't know, right? But in the data set we are given, we have 7 classes, and therefore we know the best algorithm that we can learn will try to distinguish between those 7 classes. Right? There are other issues such as class imbalance and all that, but that's the fundamental thing in classification. In clustering, we have no such universal knowledge, right? So in that, if you look at this class, now we have 14 of you, right? What is the right clustering of you? I know we are predisposed, or we are kind of biased towards thinking of certain clusterings. And I will say the most common clustering we will say is a male and female. So that means 2 clusters. But that certainly is not the only clustering they can have, right? Number 1, it depends on what the data we are given. In fact, clustering by gender is by data such as, I don't know, the subjects you're doing, or where you live, things like that, or your name, or your age. Is impossible virtually to cluster into the 2 genders, right? So how many clusters you have will depend on what data you're given and how relevant they are for your purpose. So what is the purpose? Right. So you may say, right, yeah, but if you give physical features like the dress you wear, or length of your hair, and things like that, but well, it still doesn't isn't guaranteed to give you a cluster of gender, right? So in fact, it all depends on the purpose, how many clusters we want, right? And in general, it's also dependent on how many our brain can handle. So if I tell you, right, okay, actually, let's say not this class because there are only 14 of you, but let's say your whole batch, not the current batch, but the batch that started the degree, which is, I think, 100 of you. 100 of you. I say the 100 of you fall into 17 categories, right? 17 clusters. Actually, it turns out that our brain can't really process that so well. There is some rule of thumb like 5 plus or minus 2 and things like that. But in general, we can handle binary variables very well. Right? Ternary or 3 clusters, yes, 4, 5. Somewhere beyond about 10 or 12 or something, it becomes less informative for us. So if I say there are 17 clusters, you will say, okay, that's fine. But what are like the higher level clusters? So that's why hierarchical clustering is good for that. So are there any higher level clusters? So yeah, okay, these 17 fall into 3 categories. So let me say, it turns out that the 17 that I first meant was 17 districts you come from, right? And I can, of course, give a higher level thing of, let's say, 9 provinces, or maybe there aren't some people from 2 provinces, so only 7. So now that is a little easier to handle, right? 7. And then I can further kind of say, okay, those in I don't know, at one point there were district boundaries about. So if we wanted to find out how many can come into campus, when there was a district boundary, we would want to know how many are within the Colombo district limits and how many are outside. So just a binary classification, categorization. Right. So there is I will upload this zoo data file, right? Gives a good idea, because there are a certain number of zoo animals and certain types of zoo animals. Right? And what I want you to do is to see how you can use the data that are given for them, the attributes that are given to them, to try and cluster them into without using that biological type. Right? Type means, so I have forgotten exactly how many types there are, right? But let's say there are 50 animals falling into, I don't know, 11 types or something. But without using that type data, we are trying to see from the attributes, what kind of clusters can I get? That will show you. So what I want you to do is to exploit, I have just said, initially using only the first 2 attributes, right? Which are hair and feathers. Can you do a hierarchical cluster? And then do a box plot is one of the easiest ways to see how the clustering has happened. You box plot the cluster that is the predicted cluster of the animals against the type. Right? That will give you how good your, well, not exactly how good your clustering is, but probably you know that the biological clustering doesn't the given features, obviously these 2 features alone are insufficient to generate this. But it turns out that even if you add some of the other features, so I asked you then to add any 5 features in order to make this clustering better. And even if you use all the features, the best number of clusters may not be the number of types. That's quite that's a big problem, right? Because we know from biological data that they fall into these so-called types. Let's say, I don't know, mammals, reptiles, birds, fish, and so on. But using the features, there are quite a lot of features there. It may be not possible to get our clusters exactly mapping onto the types, right? So the main takeaway from this thing on clustering is that to know that clustering is not is hard to say right or wrong, but you can of course say this is a better or worse. I think I have exhausted my 90 minutes, but I will very quickly also talk about k-means clustering. Right? So the thing is that when you have very large data sets, hierarchical clustering is quite expensive, right? And therefore we use k-means, right? Probably one of the most scalable algorithms for clustering. Tries to split the data into, the negative thing is that you have to specify k. And this is another big problem for most people who are used to classification. Because there we know the number of classes. Here we don't know. So let's say we have an idea, right? We know that this data falls into k number of clusters. So the algorithm basically is very simple. You select k centers or centroids randomly in the data set. So we have the data set like this, and randomly we select, let's say if k is 3, we select 3 random centers. Then assign each point, so there'll be points here all over. Assign each point to the closest center. So we assign them to, so these are the cluster centers now, and we assign everything that is to that closest cluster center. And then we recompute new cluster centers. So for instance, if most of the things that were close to this were not on this side, but they were on this side, it will pull this cluster center more towards that side. I will also put a link to a animation of this. And then we recompute the new clusters and we repeat this process. Right? We repeat this process until there is no change in the cluster membership. Right? And these centers stabilize fairly fast. Convergence happens fairly fast. So it still leaves the question open: how do we select k? Right? And this baffles a lot of people. So if you think about it, we would like a k value that results in the smallest possible distances within a cluster. That means the items in a cluster are close together, and largest possible distance between points in different clusters. Okay, if we this is the more common thing, and it's referred to as within cluster sum of squares, or sometimes simply as sum of squared errors. Sorry, my writing is very hard with this trackpad. So sum of squared errors, and we plot for different k values. For k is 1, we don't consider that case, because if the whole data set belongs to one cluster, then there's no interesting thing there. But we try for k equals 2, 3, etc. up to, let's say, 10 or 12 or something. Right? If you think about it, let's say there are 100 data points. If we draw this up to 100, and since this is the sum of squared error, if we draw this x-axis up to 100, at 100, sum of squared errors will be 0. Right? And we like that. Right? That means we like the smallest possible distance between points in the same cluster. So if there is only one data point in each cluster, that means the sum of squared error is 0. Right? So obviously, that's not how we can detect. But what we detect is, let's say there is sum of squared errors is here for number 2, and then it comes down for number 3, and then it straightens a bit for number 4 and 5 and 6, and then it straightens some more for 7. So these points we call elbow points, right? And they point to, these inflection points are the more plausible number of clusters. And having multiple of these is okay, because we saw in hierarchical clustering, we can explain the data set in multiple places. So it does fall into 3, but it also falls into 7 more fine-grained ones. Right? So this is just using sum of squared errors, and this is called an elbow plot. Right? And this is a common way, common quick and dirty way. But if you want to combine this with the fact that each cluster is far apart, we compute something called the silhouette coefficient. And we would want the silhouette coefficient. Silhouette coefficient doesn't behave like this, right? It's a number between 0 and 1. And the closer to 1, the better. So here also k will be 2, 3, and so on, right? And so we want to plot, and hopefully there will be things like this. At let's say 3 and at 7 maybe. Like peaks. Higher the average silhouette score, the better the clustering is. So these are both called internal or intrinsic measures of cluster quality, right? Yeah, here I'm talking about what is a reasonable range to check for k, right? Usually we do like say 2 to 10 or 2 to 12, or depending on the nature of the data. I've just asked why not 1. It's fairly obvious. But so the issue here is that k-means is not guaranteed to find the optimal k this way, right? One of the reasons is that the clustering depends quite a lot on the initial centroids. So if you do k-means several times, you will get different numbers of clusters as the best, and different clusters also. Right. So one thing is to keep running it multiple times, right? And some widgets have something called reruns, where you can specify how many times to run an average. Another way is to make sure that your points, your initial weights are, your initial centroids are, let's say, not all in one corner like this. Like your initial centroids are spread out, and that we do by k-means plus initialization. And then, of course, we can validate or visualize our clustering using some kind of scatter plot widget. Right? It's important to know that k-means will always find clusters, even if there aren't any. So, classical thing is if you have a data set where there are dots kind of spread out evenly everywhere, right? K-means will still try to find the number of clusters you specify. If you say K2, it will divide this into 2 clusters because it's of the nature of the algorithm. It starts with centroids, right? So it will place the centroids, 2 centroids randomly somewhere, and then they will it will do some kind of a find 2 clusters. Right, I have said try painting data in a single large cluster. I mean, if you can generate some random data like this and you try it, you will still get some clustering. So, of course, that's why in clustering, normally we try more than one clustering algorithm often. We may try hierarchical and k-means. Or if the data, there are some kinds of data where the data is kind of all bunched up together, right? And so for that kind of data, we can use density-based clustering methods such as dbScan or HDBScan, things like that. So you can see, you can check on RapidMiner what are the clustering algorithms there are. And try, let's say for the zoo data, can you use one of the other clustering algorithms to get a better clustering? So for most distance metrics, we use standardization of the data before as a pre-process. The reason is that otherwise certain, let's say you have one, for distance measures, any algorithm that uses distance measures, that means all clustering algorithms and some classification algorithms such as k nearest neighbor, right, which depends on the distance. For those, you need to do some standardization. Otherwise, the higher, like those variables that have bigger, let's say there can be a variable that has all values between 0.1 and 0.6 or something, and another variable that has values between 1000 and 3500 or something. Right? So those are going to dominate these. So because of that, you need to do standardization. Nominal features need to be converted to binary features. So if you have more than 2 categories, you have to convert to multiple binary classification features and so on. And ordinal features need to be converted to numeric values. Ordinal means like high income, middle income, low income. That's an ordinal feature. So you have to make it 1, 2, 3 or something. Right? And of course, many of these are done automatically in your clustering widgets. By the way, widget is the term we use for one of those components, right, in our pipeline. Right, so the advantage of k-means is very easy to understand and to implement. Actually, you can write k-means. Right? You don't want to do it because you don't want to, bug fix and all that. And it's very efficient, can handle very large data, and by far the most popular clustering algorithm. The disadvantage is that it converges to a local optimal. and it needs to define the mean. Right, some notion of an average. It is sensitive to outliers in the data. Right? If you can create an artificial data set and then cluster it, and then you just put one data point far away, and you see the clustering becomes really, really different. And it's sensitive to the initial seeds, so you need to repeat the process and maybe do something like k-means plus initialization. Now there is another unsupervised technique called dimensionality reduction. Not sure whether we'll have time to talk about this. Let me see a show of hands. How many of you have come across this idea of dimensionality reduction? Can you raise your hands? I'm going to explain it anyway, but I just want to know. Okay, Iromi, where did you come across that, in your project or in a course?
Both in the project and PCA was taught in the data analysis.
Okay, right. Thank you. So, why do we need this? We need for two reasons, right? One is visualizing, one is reducing noise. So you can imagine you have a data set that has 17 dimensions or 17 variables or features, and you do a clustering, and you're totally reliant on the silhouette score or the sum of squared errors for the number of clusters, right? How good the clusters are, because you can't plot 17 dimensions, right? So, so if you have a way of transforming those 17 into 2 or maximum 3, then that's going to be very useful, right? So that's one reason for dimensionality reduction, visualizing the data. The second one is reducing the noise, or reducing, you have 17 features, but it turns out that some of them are what are called confounding features. In statistics, this idea is very common. So you have some independent variables, but there are some independent variables are like confounding variable. They obstruct the signal, right? So to improve the so-called signal to noise ratio, you want to reduce. And there are many techniques, right? Feature selection and feature extraction, right? You may have learned them as filter and wrapper methods, things like that, right? Yes, so as Iromi said, principal component analysis is one of the most popular things. It comes from statistics. And so in RapidMiner, you have a widget for that. And you can determine how many principal components. So this is a feature extraction method. So what it will do is transform your 17, I'm just using 17 as an example. It can be a 1000, doesn't matter. Features into one feature. Obviously, that's not going to be enough. 2 features, you can say 3 features, and so on. For visualizing, it has to be 2 or maximum 3. But for noise reduction or feature extraction, we normally look at how many components are needed to explain, I don't know, 80 or 90% of the variation in the data, right? There are also other linear algebra methods like multidimensional scaling, which is based on singular value decomposition, or non-negative matrix factorization. So you can see the kinds of things that are there in and in RapidMiner, including something that is probably very popular. And each of these they are not doing it exactly the same way. And so they are used for different purposes. T-SNE is one of the newer algorithms for doing this. Right, so this, as I said, this was this homework was set for using Orange, but I will make the Zoo dataset available for you to try these things. Okay, right. So we looked at two other kinds of data analytic things, business analytic things, right? That we want to be able to do, recommendation systems and clustering. And each of these has a learning objective. The recommendation system has the learning objective of how do you, when the chosen tool does not support your task, right? The next thing to try and look for is there an add-on or an extension or a plugin, right? So that's, you need that for recommendation systems. And in some cases, you may actually have to write that code, right? And so, or in Orange, for instance, you can have a component which is called a Python script, right? So I don't want to go into that part, right? And in RapidMiner also you can interface with code. But the thing is, for most things, either there are built-in widgets, components, or there are add-ons and extensions, right? So I don't. Unfortunately, in the world we are in, there is a lot of specialization that is needed, and so what you would end up doing is to tell a guy in the software team, okay, I need a component that does this, right? And let's say there is no k-means plus plus in RapidMiner. I haven't really checked. Then you say, okay, I know the k-means plus plus exists, and I want a component, either a component written, of course, that's then you need to know the SDK for that. That software developer has to study the SDK for RapidMiner plugins. But otherwise, you say, okay, I can read the data from RapidMiner, do this kind of thing, k-means plus plus initialization, and give control back to RapidMiner, something like that. So that's the learning outcome of the recommender system. The learning outcome from clustering is that unlike in classification, there is no kind of right answer, right? There are better answers and worse answers. So the exploration with the Zoo data set is for you to kind of realize that, right? That particular biological classification, even using all the features, and the features are supposedly relevant features for determining their type. And of course, we already know, for instance, that we are taught that a whale is a mammal, right? It's a big fish, but it's a mammal, right? Or an ostrich is a bird that can't fly. Right? So we already know some of those things, right? And you will find that the clustering algorithm using those features, right, is unable to classify in a case like that. Right? to cluster in a case like that. So the world of classification, clustering is, as I started, is a way of exploring the data rather than for finding the right model as such. Having said that, we can say that this clustering is better than that clustering. I have only shown you the intrinsic measures for measuring clusters. There are extrinsic measures. So when will you need extrinsic measures? That means you have some ground truth data. Right? So you have some ground truth data where we say, right, these are the, actually in the data set that you have, there is that ground truth data, the type in the zoo data. In many data sets, we won't have, right? So if you take the universe of data sets that you can ever collect, a vast majority will not have labels because labeling a data set is a time-consuming task, right? So the pre-labeled or annotated data sets are a small number compared to the amount of unannotated data. So how do we compare with ground truth? So let's say I have 1,000 data points. I can afford to manually annotate 200. Well, that's too close. So let's say I have, 10,000 data points, and manually annotating them is really, really hard. Or some of you may have like, I don't know, 110,000 data points, right? Then it's, you can't annotate even 10% of that, which is 11,000 data points, right? So you say, okay, I can't do that. I want to cluster them, and then I want to compare the cluster quality using internal measures, what we talked about, sum of squares, errors, elbow plot, and silhouette coefficient, and things like that. And then I'm going to manually assign classes for 500 of those, right? So you can do that and then see, okay, these 500 fell into some clusters in that clustering, but now they are annotated, right? So there are measures to compute, even if the numbers are different. Let's say my clustering came out with 7 clusters, but my manual, those 500, I classified into 5. There are measures to compare the clustering, 7 clustering with the 5 classes that you have defined, right? And they are the RAND index and the Jaccard coefficient. So in practical situations, you may have to do that, right? So if you get a good, the reason for having two measures, yeah. I mean, so these are the kind of questions I want you to raise in that forum, right? I have put a forum for all. I've said for rapid minor tasks, but it doesn't have to, I mean, anything coming out of it like this. Okay, but why do we do RAND index, and why do we do Jaccard? When do we do each of those? So that's the kind of question I want you to generate, and maybe someone from among you itself answer, right? I will also answer if nobody answers. Okay, so I've gone over the time also, right? Apologies, and good luck with the task. Please remember to designate 2 2-hour slots this week.